This is real benchmark running on my machine, and as you can see, we get on average around 780 average tokens per second. So what you saw was over 9 times more average generation than the base Qwen 3.6 20 billion in same quantization in Llama cpp. But I show it to mislead you because this is the best case example when we have the same prompt repeating over and over again. So this is the last speculative method that we don't cover in these channels. So today we'll look at what is ngram, why we should use it, what are the caveats, and then we'll do real benchmarks on it using all available benchmarks that I found, and also the custom ones to show you real workflow benefits that comes with it. I'm Łukasz, I'm the lead Gen AI engineer that specializes in AI and inference, and let's go. Let's do a reminder why generation is 1 token at a time. A large language model normally just writes 1 token, and the token could be word, part of the word, or just punctuation. And here on this example, we can see that each time new token is added, which is marked as blue, then we need to add every other one before as context, which is marked by the yellow dotted field. So to generate each token, we need new pass. So to generate 5, we need 5 passes through the full context. So this is an issue because it's large and expensive at every pass. And the cost of it is at low concurrency. Much of the waiting times come from repeatedly moving the model weights through the GPU for small amount of new text. So we say that this is memory bound. Why? Because we wait for the memory with all the GPU utilization and possibility of doing high computations because it's not yet in the memory. The speculative decoding tries to be more useful and generates much more text or tokens at one pass. Now we'll have a quick reminder of speculative decoding. So speculative decoding is guessing first and then verifying once. So we have a smaller model, which is a cheaper guesser. This is typically named a draft model, and it proposes several tokens. And the target model, so the big model, check all positions together in one pass. So here we have the drafter guesses. The capital of Spain is Madrid, which is 6 neutral guesses. And then we have the target verification. It accepts 3 first tokens, and then it don't accept the Spain. And because it don't accept it, we need to delete all of these tokens. And now when we send the output, we are still in the decoding phase. We can add 1 more token, so the capital of France. So we get 4 tokens together. If you want it to more explained, because this is related to DFlash, then there was video about it that will be linked down below. So who is in charge? The drafter is never the authority. The target model always determines the committed token, and the correction comes also from the same verification pass. So that's why we say these methods are lossless, because the big model that was generating token is checking the propositions. So that's why we shouldn't lose the quality if the implementation is right. So as I said, this is quick DFlash recap if you don't want to check the video. It doesn't search for early text, it just predicts a block of future tokens from current context. So we have context, the DFlash predict a block, and in the case of Llama cpp current implementation, it's up to 15 tokens, and then check all together by the main model, which in our case will be Qwen 3.6 27b. And then all guesses appear together in one parallel proposal. We accept this, we reject them, and then we add the response. And if you are interested, you can check my last video when we check the DFlash with Qwen model. And in this video, we'll look into DFlash with ngram. And take note, the block size is 16 because we count 15 drafts plus 1 generated. So it's 16 together. Now let's look at what is the ngram. So ngram is simply a copy machine. We look at the sequence of several tokens and we ask, have we seen this exact pattern before? And here we can see we have name Alice, role admin, active, true. So we see this pattern, the yellow mark, and then we guess that that's now our next guess that it could be true. And now if we recognize the same pattern in the completely new part of code, then we suggest that it's true. This is only suggestion, not committed. Why? So that's why it will be lossless, because we steer the big model that decides if this is true or false. And why matching similar things for us, it's not exactly the same matching for the LLM. So user and users, if you look quickly through it, you will see, it's very similar, but the tokens are just numbers for the AI. So this is what AI see. So this is unrelated then for the AI. That's why we will not match this pattern. And the key idea is that basically it's copy-paste with a memory. So it's useful for JSON, for templates, repeated code, rewriting documents. Now let's look at more complicated examples. So the ngram-mod. So this work like following a trail of breadcrumbs or anything. So here we can see we have pattern A, B, C, and then we accept the D and we will add it. So now how it will look like. We added D, so I is no longer added because it's lookup window, so it moves. And then we C, E, we added, so we move by one, so B will be no longer in lookup window, and we added the tokens. And all of these tokens are not added, they are just temporary draft, so they got not accepted yet. And the context itself never changes. So we use the latest pattern to recall one token, move the window, repeat a temporary draft, add one remembered token at a time. And now let's look how it looks with llama.cpp settings. So we have ngram-mod with 24 key, and we want to build 4864 tokens new. So now we will have the 24 tokens are the latest tokens already written by the model. They remain unchanged and are only used as a lookup key. Then we do the lookup, and if the memory recalls the next token, that token enters the temporary draft and the windows move forward and the process repeat as we said. And the chain must be built up to 48. This is value as a parameter. And then the maximum is 64. Now let's look how it will work. If at 31, the next token will not be accepted, then we discard the temporary draft and we write the next one. If then we go over 48, because that's the minimum, that's not when we will submit it, we basically then look, and if it breaks around this range, then we just submit what was generated before it was not accepted. Or if it achieved the maximum window of 64, then it's also accepted. So as we can see, if 55 token proposed, that means that we accepted all of these tokens. Now let's look at more complex technique, which is ngram-map So we have detection of one pattern and we'll look for several endings. So ngram uses the latest 12 already written tokens as a key. We have here the tokens and we see the status. And when the exact key appeared before, it remembers up to 4 different continuations that follow it. And we can see it here and how many times they are found. So here the success continuation appeared 8 times, the alternatives 2, 1, and 1. In the Llama cpp build used for this test, the winner must be at least twice the alternatives combined. So 8 will qualify. And this is still experimental, so this could be changed. And if there is no ending that is multiply of 2 of the rest, then we will not have a draft and we will look into the other methods. Now let's look into more details. We have the parameters here. So for example, we have spec ngram-map K4V size n, and this is the size that we already written for the lookup key, so the 12. And then we will point to these endings that we defined before, that this one was 8 times. And now let's look what are the conditions. We have the minimum hit condition, so the key must have appeared at least once before the current position for this to trigger. If the K is not seen before, we will have no draft. And if there is no dominant continuation, then we also don't have draft. And dominant, which means the dominant of 8, so the 2 times more than the rest, and we have hit over 1, then the target bit model verifies it, and if it's verified, so now let's see how it works. So we propose 48 tokens, but model accepts only 10. And then we'll store these 10 accepted tokens, and in next use, we will cap the candidates to 10. And this behavior is commit specific, so it could be changed in the future. Now let's look how all of these methods work with each other. This is actually a priority ladder. So we have the draft router in the current Llama cpp build that I use. And first it checks the ngram-mod K4V. And if there is draft available, then it will be sent to the target model to verify. If there is nothing here proposed, then we go to ngram-mod. And if there is no draft available, then we use DFlash as fallback attempt. And this actually makes sense because these methods just work on memory. They are cheap to work. And this is not as cheap through the utilization. And now let's check. If, for example, we have different workloads like novel explanation, then DFlash will get the round. If we have repeated JSON, then K4V will draft us something and will skip the DFlash. And if we have rolling code rewrite, then the mod one will be used. So basically, the first non-empty draft wins the round. So it's like a copy machine that stands in front of a smart guesser, and when it recognizes something, it goes first because it's cheap. So as you can see, we have two different guessing problems. One predict new text and one reuse old text. So it's the same goal, but very different information. So DFlash is the learned predictor. It predicts from context, works on novel text, does not require exact repetition, but it only proposed up to 15 tokens here, and it costs a draft model pass on every round. So it's basically favored by open-ended explanation, conversation, reasoning, and creative wording. And then ngram is the copy machine, so it searches exact token patterns, so it needs repetition, it kicks out later, but it may produce nothing at all. But it can propose 48, 64 tokens here, and there is drafting cost that is not as big. So as I said, it's cheap memory lookup, and it's favored by formats like JSON, template, filling, and code rewrites. Now let's set expectations. That's not universal speedup number, but the combined setup value rises and falls with the amount of reusable text and context. More draft tokens is unequal of more speed, because a 64 token draft is not 64 tokens of progress. It's the accepted part that counts. So if we propose 64 and accept 61, we'll get excellent round. But can also propose 64 and get only 3. So we verify the long draft for almost nothing. Then we can have efficient one like 50 proposed and 10 accepted. So shorter draft with good accepted progress. So the real speed is accepted tokens divided by round time. But we also need to take into account drafting time, verification time, accepted progress, and this will equal to real performance. So the best drafter produced the most accepted text for the least amount of time. So now let's jump to the most sexy part, benchmark setup. So basically we use the same model as in the video before. If you don't know, you can check it out with DFlash. And then this will be Qwen 3.6 27 billion, Q4KXL quantization, 6000 Pro, same Llama cpp 13 build, same deployment in Docker, the greedy temperature 0 for as much repetitiveness. We will have the test of base model, the DFlash, and the all ngram combinations. And basically we do restart, run workload, record, repeat, and compare. So now let's go to the benchmarks. In the last video, when we compared only DFlash with base model, we do only 100 examples, and I repeated this test to be sure that everything is right, and we use grid decoding, so the highest probability, but there is still a bit difference in the scores and how it runs, because yeah, probability. But as you can see, we do 500 problems from algebra, counting, geometry, intermediate algebra, number theory, pre-algebra, and pre-calculus. And the scores are very good and practically in the same range. It jumps sometimes for the DFlash, sometimes for base, but overall pretty good. Then the interesting part here, the average pass rate is 88% to 87%. But the generation speed is 3.5 times faster for the DFlash. And I don't run it for ngram in this case because we only were testing if it's lossless. And as we see, these methods are lossless as per the Lamma cpp setup. So we'll not need to test the ngram, but we don't test decoding last time because I couldn't run the benchmark, and I added the LCB coding dataset. The main task that most people use, Qwen 3.6 with 7 billion, is coding. So last time we tried to run it and I tried to fix it in aiperf, but I think there is still issues related to it. So I used the official repo of LiveCodeBench to run it again with the temperature 0 with highest probability rate. And as we can see, we have similar scores of 20% for DFlash and 90 for base. And the score is a bit low. And why? Well, we don't use reasoning. And also from what I see, it's test that executes the code and so on. And we use the quant, so the score will not be as good as the original model in full size. And yeah, I don't use reasoning because it tends to overthink, and running all these tests is then very long, because if it goes into one loop, it will burn every possible token and so on. That comes from multiple tests that we do over this channel, so you can check them out in the description. And also with the hardness of the test, it sometimes cut the 2000 token cap while using the model, so there are like a bit of issues there, but it was on 2 cases, but that's just what I found. And I only use 58 problems because yeah, it takes very long, and we have heat wave in Europe, so I need to run AC while running this test to not overheat GPU. So yeah. So now the ngram comparison. So we check the accuracy and we see it's as expected, but now we want to test ngram. So I ran the full stack with all the methods that we described, so the map and mod, on the live code benchmark, and the results are interesting. So as we can start from the left, the draft acceptance is higher for DFlash. And why it happened? Well, it's because it's various different coding tasks, so there is not much for ngram to basically benefit. And even if it proposed, the overall acceptance rate will be lower. Why? Because DFlash is the last one in priority, so the ngram will basically work before it, and that's why the draft acceptance is lower. We tested it on 100 problems. I modified the official LiveCodeBench GitHub repo so I can run it through aiperf, and we do again the same concurrency with the same seed. And as we can see, we generate less tokens per user on average for ngram 2. The intern token latency is also lower for DFlash, which is better. And then the time to first token is basically 2 times. Its time to second token is basically 2 times lower. So as we can see, if we have 100 different various tasks, then yeah, this provides overhead, and maybe it's not the best to turn it on. But that's not how we do it. Yeah, we typically work on iteration of the code, or we, for example, edit something and we add more things, more prompts on the same questions. That's at least how I use it. So yeah, as I said, we typically don't use ngram when we do different things, yeah, like 100 different coding examples. I mean, maybe you use it, but we know. So we need benchmark that will test the actual workflow with the context that is getting filled, and we chance it along as we go. So I created my own benchmark because I couldn't find any to run it. So we'll create an 18 prompt suite, and we'll send it as one cumulative conversation in a few phases. So we have first phase with 9 prompts when the model creates a Gradio chat app that extends the same code, based feature by feature, history, settings, stats. And then we do 10, 18 prompts which are realistic vibe coding follow-ups on the finished app with full remission, don't strings renames, make book reports, refactor, playtest, and a small feature review and fix readme. So the model will keep re-emitting and modifying its own prior code, exactly the iterative coding scenario where ngram drafters should help, or not. And the main phase is where the advantage should peak, so aggregates the reported phase and overall. And we'll have the workflow now. So we start here, the Docker service that we choose. You can run this as UV-run benchmark, so you can test it yourself and modify. And then we basically swap service and run it again. And then we compare every result is stored in JSON. It will be in the description in GitHub repo as below. And I will use full context for it because, yeah, I want to see as much as possible. And I don't know how many exactly code will be provided after so many prompts. So we can see here are example prompts, build gradio chat, and so on. Add stop button that cancels in-flight stream, the generate button that reruns the last. So this is our own benchmark that will run. But as I mentioned, it will be on Dockers. So where they are. So as before, guys, I packed everything in this one Docker. So you have Lamma cpp with DFlash. You can just click here to run it. And as you can see, I execute this command because I have plugin that you can get by going to extensions and to Docker. This is the one you need. So this is starting, and we can see here that the Docker started and everything works. Yeah. So we can stop it. So here we specify the number of drafters, but this we described before. We have the baseline model that you can also run, and we have still the MTP model that we also tested. It could be also useful for some use cases. Basically, DFlash is a new support, so most models don't support it, but then you can have MTP and you can specify more heads here actually, but it's not as beneficial. Typically 2, 4, 5 are recommended depending on your resources and hardware. And then we have the DFlash. So as we can see, we specify the draft repo and the draft file that we'll use. This is the one that we described in last video also. And as we can see, we have the setup. So the spec type, I talked about it before. We specify basically each speculative method that we want to use, but the order here don't take any priority. It's as I described before. And there's a lot of numbers here to play, and it's a lot of experimental. So I choose all the default ones just to test, because playing with it's really depending on specific use case and so on, and it will require a lot of tests. I check the KV cage, but basically there is slowdown, so it will be not necessary. And maybe we can run it before I go to the benchmarks, and we can run the leaderboard to see how fast it is. So leaderboard is the test that I also write, but it's pretty simple, but it just do nice animations. So as we can see, I have too many runs. Because we run here the same prompt, we basically can see that the tokens increase. Why? Because in the ngram, we use the same tokens, so the ngram methods basically get crazy amount of acceptance. And as we can see, because it's same token, and as we can see, because we run the same prompt like 10 times, then there is no competition and the ngram is fastest here. Yeah. And this is all the results that we tested from the other tests with MTP, with reasoning, with DFlash, and so on. We can see here that technically 12 was the best, but it's just by 3 tokens. And as there are multiple processes running sometimes when I run this test, because I need to use PC, I still use 15 for most of the tests because I want to see the maximum capability, and because it's diffusion and we know how it works from my other videos, then basically there is not that much overhead to between 12 and 15. And yeah, okay, so these are the results. I put it for all 18 turns with a build, or just for the turns, so editing existing code. So we see the baseline was around 40, 54 and 51. Then the DFlash provide 3.7 boost with 199 and 204. And then we added all the methods separately. So the map map provided 3.8 speedup, so not that much, but then ngram-mod provided over 5.7x speedup, with much more for the turns, as we can see here. And then this is with all the methods all together. So with DFlash, ngram-mod, and map. And as you can see, it's 6x speed on continuous editing the existing code base with all the context. So as we can see, the results are quite nice. We can see that there is quite boost related to it if we use everything. But as mentioned before, if we use it for variety of coding, it provides a bit overhead. But with this Docker and with Llama cpp speed, basically you can just click it and run it. It runs in 2-3 seconds. Even less actually for me. You can just add the ngrams in the Docker, basically by just deleting it from the flag that we talked before. So now before we jump to the interesting part of the last benchmark, I want to just say that we are very close to 500 subscribers. So if you guys can help to feed the algorithm, that would be awesome, because then these videos could help more people with local AI deployment and so on. And I can't attach everything inside the GitHub repo and in the video, because then my video sounds like a few hours long. So I will try to compress it, and you can sign down below this video on the email newsletter that will just give you overview of new things happening in Inference and findings from these videos with clear visual examples. And now let's jump to the test. So as you can see, the speculative decoding versus context size. So there is very big jump, but there is a caveat here, as before. Also, if you watch my last video, this score got improved a bit. Why? Because I checked, and the aiperf, even though I specify more context that it runs, it was actually overflowing from Docker inspect when I ran it. So it was cutting some responses. That's why the DFlash couldn't speed up fully, because it couldn't produce all the tokens because it was cut midway. It will be explained in the README in more details. And the interesting part is that aiperf, if you do synthetic sweep, it uses Shakespeare as input and output, because we want synthetic input and output, so it shouldn't be repeated. But then I inspect during the run actually what's getting produced, and if we achieve a limit of tokens. So for example, we will go through the set amount of Shakespeare novel that was imputed, then it will try to add artificial constant lines. And in this case, it was from lost labor, lost continuation, and it adds constantly 2 lines of Armando, I will be faithful, and Moth, and so will I, sir. And it's repeated 1,500 times at the last bench, so on the 36K, and that's why we get 92% of draft acceptance, so a lot basically, and that's why this score is quite high. So this is related to this big of a jump, because what was happening is that basically you achieve limit of the Shakespeare that was there, and it was adding more and more. So I will investigate it, maybe put a GitHub issue, because for these techniques it's quite hard then to find a very good way to measure it. And as always, you can run all of this. There is setup UV, readme, instructions, and everything. I don't go into big details because that's typically, it's still better to see in the README yourself and just quickly run than watching the video. And now let's jump to summary. So I nearly forgot about this test, but last time we didn't exactly check it, and I thought it will be interesting to see. So this is the full context loaded with base model, the DFlash and the ngram. And as we can see, the jump is mainly for DFlash because we load the model, and then it's individual context based on implementation and so on. I suspect this value should be lowered because of the architecture of speculative decoding and the coming DSpark and other options, but this is good to just know. And as we see, ngram is basically free. In the tests, there was like a small delay on tokens, but it's in the error rate, basically because you can't run the tests without like some pre-processes going on your PC and so on. So there is always a bit of error. And we run a short prompt, which is like 512 max tokens. Then we run some story for 2048. So then third method is when we send a very big prompt, so 2,500 tokens, and we want to create 10 new functions based on the existing ones to see if ngram will get, for example, some very big jump in the memory, but I don't notice anything. So this is what could be very useful for you also to check. And now we go to summary of what we actually showed. So the target verifies everything. So this is basically lossless. We check it on map 500 and on LiveCodeBench. And the DFlash grow with context, so we have more speed up the higher we go. And the same applies for the accuracy scores. And working on code base, we have over 6x speed up overall, and with more better conditions, more repeating, we go up. And then we have, of course, higher numbers, but this is best case that will not happen a lot. We have same tokens, same quality, 1 GPU. We can run DFlash if we have the overroom, and then ngram drafters, but it's all depending on hardware implementation, how you run it. You should always remember to use the newest build and check if there are no errors there, because I can check it on one build and then you on different one, and for you will not have as good results, for example. Or in the newest one there could be fixes, but there could be also bugs. So I will link my build in the description probably and in GitHub repo. So now, if you like this video, you can check my other videos. We have very good video about the quantization, so you can understand which model to choose and why, where to look for scores and how to judge it. And also there are a lot of benchmark videos like Llama, Qwen, and also all speculative methods that are basically implemented up to this point are explained with quick visualization examples and showcases on real hardware. Don't forget to subscribe so we can break the algorithm finally. And yeah, see you in the next one.